Hello, my friends. So those of you who followed my posts last 2 years probably know that one of the inventions I talk about there are the waves that I say that I discovered and are useful in different areas of physics, where plasma physics is important, where plasma is present. So here I decided to put few slides and describe those waves, where idea came from, what I did different, how I describe them, and why they are important, where they are important too. In 2002, while doing my thesis about mode conversion and wave-particle interaction processes in the solar wind, that was the title, I was doing one of the topics, as you can guess, was the mode conversion in the solar atmosphere. So I was studying MHD equations, linear waves. The only term that was there different was inhomogeneous plasma flow term, representing the solar wind. And I was studying mode conversion in different areas of the solar atmosphere. What was surprising for me that when there was no mode conversion was expected, I could still see the density fluctuations. And it was surprising because if you take pure alpha wave simulations on the left-hand side here, and the magnetic field is along x-axis, you could see that waveform that is polarized fluctuates in y and z plane, propagates along x-axis nicely, and there is no density or longitudinal velocity fluctuations. But in the simulations, for this particular case, you could see the standing wave in the density and the longitudinal fluctuations, small, but longitudinal fluctuations are excited too. This was the result, on the right-hand side was the result of the simulation, and left-hand side is the result of the simulation when there are no inhomogeneous flow terms. But like I said, no mode coupling was expected here, and no book or no paper was mentioning these kind of fluctuations. And I asked myself, can I describe waves? I know what kind of plasma I have. I know what kind of initial wave I'm putting in the system. Can I describe this density and longitudinal fluctuations? And I did. I simplified the equations, rearranged the terms, made all the terms that we are proportional to the gradient in the velocity, S parameter here. I moved on the right-hand side in the equation, in a wave equation of the density, and represented it as a force, as if this was the force that was driving the system for the density fluctuations, driving the wave equation for the density fluctuation. And I came up with the solution. You could see the density is proportional, this Kagashvili wave density was proportional to the initial alpha wave, Vy0 there, and the velocity gradient, S parameter. So what this physics was telling me is that because of the interaction of the initial alpha wave with the inhomogeneity, there were waves excited system that were very much different than existing knowledge. So I wrote these solutions in 2003, actually earlier, but in March 2003 I had a presentation at the University of California where I was as a postdoctoral fellow. These solutions appeared in Physics of Plasma in 2006 and 2007. In addition to the density fluctuation, I also saw that if I would take the difference between the alpha wave and the physical process simulated by those equations with the shear flow present, I could see density fluctuations, longitudinal fluctuations, but the alphanic waveform in y and z plane was changing too. You could see those small fluctuations, and the difference is not zero. And even though those are very small, later I discovered that they are very important in electric field generation, non-zero phased average electric field generation that could effectively interact with particles. So because of their magnitude and because of their properties, I was already doing electric field generation and test particle simulations since 2007. Actually, in 2007, I even talked at the conference with Randy and a couple of other guys that I was seeing these electric field, huge electric fields, and this was kind of something, sideways, because this was something that no one was talking about, because no one was talking about those waves. But I wanted to describe this plasma in general. You could have different kind of plasmas. Laboratory plasma, you could have where particle motions are important, you could have MHD, you could have exotic plasmas, but I wanted to come up with the general solution, general framework that would I use for a given plasma and derive the solutions for a given fluctuation in a given system. So here is the basic idea what I came up with. If you take two equations describing the physical system, F1 and F2, the typical procedure is to take these physical variables and expand them in terms of zero-order variables that describe the background and the fluctuating variables. And after this kind of solution is substituted to those equations, you could get a set of equations 3, where linear fluctuations, the evolution of the linear fluctuations is described. This is the typical procedure in the field, or it's a mathematical procedure. What I did next was to take the second derivative of these, make it wave equations, these are one-dimensional equations, and then split the terms in those equations in such a way that left-hand side represent the plasma equations that describes the natural frequencies of this system. And the right-hand side represents all the terms that are proportional to the gradients in zero-order terms, like I did in 2003, the similar way. And then I could represent the right-hand side as the force that will drive all the waves in the system, all the natural frequency waves in the system. So you could see that the terms on the right-hand side, they have fluctuations. So it's very important to have initial fluctuation in the system, and the initial fluctuation can be wave, pulse, spike. Even the generated waves, the Skagashvili waves, can become the secondary source of other waves. And also they are proportional to the gradients in the plasma. And these gradients can be in the density, it can be in the magnetic field, it can be in the velocity, like I did, or it can be all these quantities at the same time. It depends on a plasma. Plasma in a natural environment is quite complex, and in the laboratory physics too. So what I did after 2006, in fact, doing this kind of expansion, the expansion that I suggested, how to derive those Skagashvili waves, deriving Skagashvili waves, and studying their amplitudes and their properties. And my main finding from 2002 to 2003 still stands, that initial wave characteristics and the background gradients are the ones that determine the amplitudes and properties of these Skagashvili waves. So the next procedure after deriving equations for this particular system, for me, was to take the solution, not like it was known in the field. Like solution is written in terms of you have phase, exponential, and you have the amplitude. The maximum in the laboratory plasma people did, they also considered that the phase can be changing. But unlike these, I saw that there were waves with amplitude that were proportional to the background gradient. So I represented the solution not like that. I represented the solution as a series of the terms in terms of S parameter. And the S parameter, like I said, it's the gradient in zero-order quantities. And after representing this solution, I could put back in a governing wave equations and derive the amplitudes for the A1, A2, and so on. As usual, A1 was sufficient because these parameters decrease they are small, and if you take higher order of this parameter, it becomes even smaller. So unlike the usual picture, what was expected when no mode conversion was expected. You have alpha wave propagates, and it just maintains its form because it doesn't match the frequency of the other waves that are in the plasma. Now I would have more complex picture. I have alpha waves, and because they interact with the inhomogeneity, I would have excited waves with all natural frequencies in the system, and the amplitudes A1s and A2s I could determine using the procedure framework that I presented in a previous slide. So what are the applications? The first application was density fluctuations. I saw density fluctuations in the system, and in the solar plasma, after publishing these papers, in the solar plasma, it is believed that it is alpha wave that carry the energy from the lower layers of the solar atmosphere. And as they transport this energy, they propagate upwards into solar wind and then interact with the Earth geospace. But detecting the amplitudes of the alpha waves close to the sun is very difficult because it was believed that they don't excite density fluctuations, and because they don't excite density fluctuations, it's very hard to measure. It's very hard to bring the instruments close to the sun, so it has to be some kind of imaging. And that's why determining the amplitudes of the waves that don't excite the density is difficult. So, but after discovering these waves, I thought instead of using the regular heliosmology tools, one could imagine the picture, very natural picture, when alpha wave propagates, interacts with the complex solar plasma, and because of the gradients, it generates the density fluctuations. And if these density fluctuations are strong enough, they can be detected. And from the detected fluctuations, one can derive properties of the alpha wave. So this was one of the first things that I proposed in 2008. Similar kind of problems with density enhancement in the solar atmosphere, coronal gels, specules. Well, that was my focus. But you can see that density fluctuations would appear in many different plasmas, but my focus where I was applying for a grant, the first application was related to the density fluctuations. And even in 2007, I had a proposal, solar wind magnetospheric interaction, because you have solar wind interacting with the Earth magnetic field, and solar wind is loaded with the alphanic waves. And because you have an obstacle, natural obstacle, you would expect that these density fluctuations would generate there and they would create the jets. Now I know that some people are doing already simulations, never mentioning my work like many others did, of course. Another application was velocity and magnetic field fluctuations. Those components were small. These fluctuations were deviating the original alphanic waveform, changing alphanic waveform, and they were very important to create non-zero phased average electric field. And like I said, all natural frequencies are present in the Kagashvili waves, and they have different amplitudes. It depends on the plasma, initial driver. And I also showed that they create how the double layers are created in 2012. Showed the non-zero phased average field along background magnetic field. And also, this process contributes in the heating and acceleration. And fusion plasma is the same. Maintaining stability of the plasma, one needs to avoid any kind of sources of the heating. When the heating is created, it destroys the stability and the system becomes unstable. So this physics is important there too. But most importantly, for all these applications that I described, one of the biggest applications of these waves was this. In a lot of plasmas, in the fusion plasma, in the solar wind modeling, for 30 years, people were using equations and ignoring the ones that we are not surviving without the alpha waves. Why? Because all other waves would dissipate very quickly, and without having the source of those waves in the solar wind, they were not important. At least this was the thought. The same thing in fusion plasma modeling equations. But as soon as I discovered this wave, I realized that if you have not only Alfvén waves and you have other waves generated that make those neglected terms important, then keeping those terms in order to understand the plasma properly, its behavior more accurately, describe accurately, then you have to keep those terms. And this was actually in 2009 when, for the Air Force, I wrote the white paper saying that, look, in the solar wind modeling equations, no one considers this. And I just discovered these waves. These waves make those neglected equations important, and I want to run these equations. Physics. It took actually 5 years, almost 5 years, 4 years, until 4.5 years, until community discovered, and a lot of people who were doing this simulation, I said, look, your equations are not accurate. Here are the terms. They are not considered. They just put those equations in their modeling equations. Thank you, and we don't need you, and they don't even they don't even reference that. So you can judge the community by that. Sorry, this is where I will stop and will not continue. For those unholy thoughts that come to my mind, you could read my posts, and I just write in my heart there. Here's one of the last examples. What was happening since I discovered these waves? I would see some kind of application. I would write someone, look, here are the waves, and they can describe what you see. It's not a mystery. Why don't we, collaborate or, something together? But a lot of times, things we are like I'm describing right now. Jack Gosling, retired from Los Alamos, now at LASP, Colorado. Big institution. Both institutions get a lot of money. LAN actually gets, I forgot what is the budget, maybe it was 4 billion or something. I can be wrong, but it's billions. So in May 2015, he published Astrophysical Journal letters about the pulsed Alfvén waves, unusual waves, Alfvén waves that he saw in the solar wind data. I wrote to him. He says it's uncertain, the origin is uncertain, and it's kind of, letter, and probably he got even more money to, study this letter. I wrote to him, look, here are my works, and look at those waves, Kagashvili waves, they might hold the key. He never replied, and I'm not surprised because I talked to people from LAN and LASP, and they are the same. And here is the equation. I don't even change the parameters from the simulations that I showed like on a second slide. It's the same simulation. The only difference is what I did, I just split the fluctuations in terms of Alfvén wave and Kagashvili waves. And the first row shows the Alfvén wave, and the very first picture that shows the circle, it shows the polarization plane, Y and Z, for the Alfvén wave. So if it is the Alfvén wave, and it is Alfvén wave, the part that I'm plotting there, it will never leave this circle. It will just linearly increase and decrease, but will be within this circle. But if the wave leaves this circle, polarization changes and has a little x component, so deviates from the Alfvénic, then the circle will become red. And now I'm running this simulation. I'm starting with initial Alfvén wave, and I have the velocity shear in the system. And you can see that the first row shows the pure Alfvén wave, everything like it is expected. And the second row shows the Kagashvili wave fluctuations. And you could see the pulsation. The wave vector comes out of the plane, goes inside the plane, and you could see how different are those characteristics. And they will be different because, like I said, there are 6 waves present there. And the initial amplitude, what you put initially, that drives this system. And the amplitude, the magnitude of the zero-order gradients will determine the amplitudes of these individual components. And you can guess for a different kind of input, you can get different kind of output, different variety of possibilities. So you could see it's a pulsation I thought it was a natural explanation. Why don't try to find what kind of initial wave one has to put in the system to generate what Jack was seeing in the simulation? He never replied. You could check how much money he's getting from that. I thought that people getting money from the government, they have to be more kind of responsible, have to respond at least, and be interested in the physics, what they are reporting. So that's about it, and this is kind of one of the stories. I just put some of the names from the leadership, that we are holding leadership positions when I first proposed this, James and Marcus in 2008. I wrote to them, and I think I'm writing my post. I will not go there. Jeff, who was distributing money starting 2009 from NASA. I will just hold myself, all those unholy thoughts that come to my mind, but I can just show the link after Jeff Newmark. You can see the link. You can go there and actually buy his picture. He's in the middle, making during the press conference, and the website will say you can pay $19 for that picture that you can use for your private use, personal use. And the reason I'm saying is that this $19 is exactly $19 more than the money I got for this research. And then you do the math. That's about it. I'm writing to many journalists, many people who care about science, and I really expect those people will write me. They will write me and they will be interested. Why? What happened? What went wrong? And I'm really looking forward to it. Thank you again.